Hello and welcome to the stream. My name is Nick Larson. Today is the 30th of May 2019, and today is a good day. Pretty much like every day, but today is a good day. We're getting right back. I do this every time. I always forget to update the freaking number. 7. Update. Okay. um I want to get into what we're going to do today. We've been working on decision tree stuff. We're going to keep working on decision tree stuff. Performance still isn't quite where we need it to be. We're at about 220. Well, we were at 220. And we need to be at about 45, ideally. Might be able to finagle a little bit more, depending on how close we get to the deadline for when this is due. But for all intents and purposes, we really need to be at like 45. So yesterday, I was trying to improve cache locality through reordering of the features that go into the input of this. Well, it turns out that that's not really that smart. I mean, the long and short of it. It turns out, though, that just wasn't really the problem. It was a bit of a red herring, so to speak. And what the problem is that I was only considering a really small part of what was happening. But the reality is that when you consider the whole thing, it really just kind of jumped out at you. It is a cache locality problem. The way that it was a cache locality problem is not what I expected it to be. So just think about this for a second. You have, let's just go look at the code and see how the code is doing it. And then I'll show you exactly how I came to this conclusion. The test. There it is. Okay, so what we do is we say for sample in samples, go evaluate the probability, and a sample is a job to user combination. And what we're doing is we're saying go evaluate this job to user combination. And the way that we evaluate it, and then put this into, the result array, and then do it over and over and over again until we've done it enough times. What this is actually doing under the hood, of course, is it is going tree by tree. Hey, what's up, Hugo Doll? Hey, you're going to like this one. Big improvement this morning. I'm getting around to explaining it at this very moment. So to rewind a minute, cache locality turns out to be the problem. What was not the problem was reordering of the features. The reordering of the features was like a bit of a red herring because it happened inside the actual evaluate function. This is like the very smallest unit, but it turns out that if we step back one level, and let me just pull these out. If we step back one level and take a look at these, what this is doing is saying for each tree, go and run this evaluate function. And we're calling this in the actual test, We're calling this in the actual test 10,000 times, right? So 10,000 times right here at this very top level, we are calling this function that goes through every single tree. It turns out that these trees are not exactly lightweight. These trees have this giant array of nodes in them, and this is where the cache locality problem is. What we're doing is we're loading one tree and all of this data, and then we're throwing it away, loading the next tree, doing all of the data, throwing it away, doing the next tree, all of the data, throwing the next tree, all of the data. It's not the features of the user that were the problem and like sort of trying to sneak between them. what it was is that for every single job user combination, we're throwing away all of this tree data. Hey, what's up, Ryan Roberts? And so instead, I said, what if we just load one tree run one time and we do it for all of the jobs? And that's where I had my inspiration, and so I added a second function to evaluate inside of XGBoost that says, okay, give me all of the jobs at one time, then let's load up a tree one time and do it for all of the jobs. And then what we ended up with is you only end up loading up this huge amount of heavy tree information a single time. And this turns out to make quite a big difference. So previously we were at like 220-ish milliseconds, and if I run this now, which we're going to have to pull up the to-do, put this over here, copy this, and if I run it now, cd fast.modeling.test cs, nope, .NET build, C release. All right. If I run it now, then we see where we got down from 260 to about, I'm sorry, from 220 to about 160. And this seems a little bit high to me at the moment. So that was a huge improvement. I don't know what it is. 60 out of 220, so maybe like a 30, maybe like a 22% improvement. I mean, it's a big improvement. And this gets us down to a factor of 3 of where we need to be, just about. You know, a little bit more than a factor of 3. Really felt like it was in the 130s earlier, which makes me think I have done something, like I changed something and forgot to fix it. False branch, nodes. I can't remember. Looks okay. Creating them. XGBoost. Yeah, okay. Well, anyway, maybe it was just a bad run. Or you know what it is? I can almost tell you what it is. It's because I am streaming, and streaming is eating up those processors. That's going to be, yeah, 141. Okay, so that was a big difference. You can see that, like, if it gets on a good processor, it's going to have a much better runtime. I think when I was doing it offline, it was about 130 to about 135 on average. So huge improvement. Almost, well, let's just do the math. 140 divided by 220. Was that a 37% improvement? I would take a 37% improvement, a 36% improvement. That's a big improvement. So we are doing really well, and we're within a factor of 3 here of where we want to be. So hooray, we have made notable progress. So now I'm going to spend today and do basically what we had talked about yesterday, which is I'm going to just build and compile these trees and get rid of these arrays altogether. So I'm going to load a tree one time. A tree is basically going to be a function, and we're going to call that function a bunch of times over and over and over and over again. And because we're going to call that one, we're not going to have to worry about this data at all. And I'm hoping that this effectively pushes up a couple of the branches and gets rid of a couple of the branches. Like on average, about 1 or 2 branches per tree. And if that turns out to be right, then this is going to hopefully be a lot faster. That's the plan. And then at that point, you know, we'll see. So we're going to use Sigil for this. I don't know how to use Sigil, so I am learning this as we go. Let me pull this up here. Sigil. This is it. Made by my boss, as it turns out. Okay. So Do I have plans for the summer? I sort of do and I sort of don't. Plans for the summer are almost entirely play with my kids, and we are going to go to the beach for a week in July, and then outside of that, not really doing a whole lot of anything. What are you doing, Ryan? All right. Yeah, it is pretty snazzy. I don't, like I said though, I have never used it. I have used plenty of things that do use this. I just don't know how to use this, so we're gonna figure that out. The following code only allocates a single local. Load local. A. Wait. Using A equals declare local A. 1. Load local. Okay, so basically what we do, I wish instead of things like add, like my method, he would have it be called something like add. Learn OOP, data structure, fundamentals, and coding. Just doing everything I can to be successful in my CS career. I have found some good researches for free, and YouTube is nice for visuals, and then create some project. I mean, it sounds like you're going to have a really busy summer, man. I wish you the best of luck with that. I still have every intention of answering your question. I'm going to answer it on Monday, on stream during Mentorship Monday. All right. So we're going to create a function, and then we are going to basically add a bunch of crap to it, and then we're going to create a delegate out of it, which we can then call. Okay? And what we want to do is take in a parameter, so load argument. All right. I feel like we're going to have to know enough about like array accessing and all of that kind of stuff in order for this to do what I hope for it to do. Labels and branches. Unconditional. Load constant. Define label. Load constant 1. Emitter branch label 1. Mark label 2. Load constant. All right, so emitter, define labels, mark. The top of the stack is the first element. Mark label 3. I don't see any. Oh, branch to label 3. Add, return. Load constant 1. Load constant 2. Add. Well, I don't know. This is sort of a contrived example, I believe. All right. Begin exception block. End exception block. Catch exception block. I'm about to go to the gym. Also, how long do you stream on Mondays? Usually only for about 30 minutes to an hour. It's really just like a mentorship thing where I answer a couple of questions and then that's going to be it. But do remember to take a break and enjoy the summer as well. That's right. Do that. Absolutely do that. That's a great plan. Take care of yourself. All right. Let's see here. Oh, look at this. Can we just do this? The above is equivalent to if s equals null. S is the input. Load argument 0. load null, branch if equal. Okay, so this should not be difficult. We basically just for each one of these things. Okay. End local. Okay. Dynamic method. Load argument S. Load a null. Compare if their equal branch to input is null. Then we just return. Nope. Where is mark? I should be looking for a mark. Mark label. Input is null. Type dot empty types. Load constant false. Return. Emitter. Mark label try call. Succeeded equals emitter dot declare local bool succeeded emitter dot begin exception block. Okay. Emitter dot call may fail. I don't actually even care about any of this stuff. Better names and call chaining. As shorthand. Don't know the IL instructions offhand. The interface on emit delegate type has longer, more descriptive names for all supported opcodes. Already familiar with IL and opcodes? Then just omit this. Also gives you the same functions. Okay. Automated opcode choice. All right, well, we're just going to pull it in and start grinding away and see if we can figure this out. So we already have the trees, so we're going to put this in decision tree, and we're going to have this be in here. So what I need to do, cd cd space fast modeling. Now I want to do .net add package sigil. Great. Added it. I wonder if it works for .NET Core. I'm sure it does. So now inside of decision tree, maybe what we want to do. Maybe what we want to do is try it in LinkPad first. Great idea. What a brilliant idea. All right, F4, add NuGet, sigil. Add. I wonder if I have to explicitly call in this .NET standard one. I'll ask him later, but for now we're just going to pull in this one. Add namespace, sigil, close. Okay. So let's take a look at one of these. And we're just going to try and do this by hand and see if it actually produces all of the values that we expect. Give me the decision tree test. Come all the way down to the bottom. Give me this right here. And then give me the decision tree itself. Like this. Okay, great. We should build it. Break, build. There is no build, just press play, I guess. Play. Alright, seems to be fine. Seems we have everything included that we need. Alright, that's what I was thinking about LinkPad for. Easy to create single node and test it rather than build the whole tree. Okay. Yeah, we'll just do it by hand, and then we'll give it a shot. So, var emitter equals back to the code sample equals emit.new dynamic method. Nope, you can stay off the network. E1. Ooh, alright, here we go. Lots of stuff. Okay, so the input to this is going to be an array. Let's go see about array accesses. Array access. Array access. Control F. Okay. Security, insights, issues, releases, branches. I don't actually know how to do this. E1. Let's just type array. Not new array. Index. Load indirect. Pops a pointer from the stack and pushes the value to the address. So maybe load indirect. And then what we need to do is put the address. I guess the other thing we could do is just look at the disassembly. Let's just do that. Let's go to dis.trace. Reflector. I want reflector. That's what I want. Okay. .NET reflector. .NET decompiler. .NET reflector. Download free trial. Download free trials. I'm not really into giving this stuff out. Yeah, how about a Gotek? That'll work. I can't tell if it's working or if it's complaining. I like legit can't tell. I feel like it's complaining. Oh, there it goes, finally. You just have to click it about 6 times. Dot peak. Oh, let's check out dot peak. Get dot peak. Download. Download? Your download. Alright, let's do that. Exit. Resharper. Dot peak. Install. Dot trace. Repair. Sure, next. Accept. Install. Good call, thank you. Appreciate that, Hugo. Alright, we're just going to basically look at how it does the function that we already have for the decision tree, and then we're going to copy that and just replace the parts of it that we need to replace. That's the plan. And then if it works, it works, and if it doesn't, you know, go complain to somebody. Products to install. Did I just tell it to install everything? I think I just told it to reinstall everything. Whoops. I will absolutely complain to the guy who wrote Sigil. It's like, what's that? What is he doing? I have this like big hope that it works. Hold on a second. I'm going to turn the light on and the fan on. It's kind of hot in here. All right. I think maybe I should not have installed ReSharper. Oops. Oh well. Yeah, this is taking some time. I could have sworn you only said install .peak and repair .trace. That's what it looked like to me. That's how they get you. I don't even think I use... Well, it wouldn't be in here. I stopped using ReSharper a while ago because it kind of slows things down. It's like... Okay, no, I'm canceling this. Yeah, I'm sure I want to cancel. It was like done with this first one that I installed in Visual Studio 2015 that I for some reason haven't uninstalled from my machine yet. Canceling. Wow, my lord, it takes a while to cancel. It's like, what on earth could it possibly be doing? What was that other thing I installed? Should be in my downloads. Reflector. Reflector desktop? Yeah. That's the one. Sure. And let's open this one again. Peak. ReSharper 2019. Skip. What? Skip. Okay, I'm not crazy. These are all set to skip. Maybe it's because I didn't click that. Oh, there you go. Let's try that one more time. Oh, that's why it's taking so long. It's downloading them. That integrated into VS. Yeah, whatever. Okay. Reflector. Close. Yep. 47. Yep. Okay. Let's go to here. Code. Culture of development. Fast. Modeling. Decision tree. Bin. Release. Net standard. Modeling. Let's try this. That didn't work. Drag and drop doesn't work. Drag and drop doesn't work. That's okay. Okay. There we go. Oh. And then you try to do something to it and it's like, no, I'm sorry, I'm busy. Let's just close this. Maybe that's the problem. This isn't particularly helpful. It's like completely frozen. It's completely frozen. Exit. Whichever one of these wins, wins. It's having a serious time. Okay. You get a chance. File was removed. Oh, wait, no, that's system. Okay, here we go. Hey, look, see, all right, this one wins. Now we just have to figure out how to get out of this one. Close. It was probably sending all of my information on my computer to some third-party server. Fast.modeling. Decision tree. Decision tree evaluate. Evaluate. Come on. There we go. Now, what I want to view is the IL. Sources from symbol files? How do I view the IL? IL. Boom. Okay, great. So this is a class, and what I care about is this method called evaluate. Decision tree node, toString, constructor, index, create, get nodes. Evaluate. All right. Load arg0. Oh shit. What just happened? That is not what I expected to have happen. There we go. Okay. Load arg. There is no this. We're getting rid of that. We're writing a function that takes a, so we don't need to load arg0. Load ld. That's first. Store location. Start of loop. Branch. BRS. I have no idea what BRS stands for. BRS. You know what I also don't see here? Oh, I see. It's doing IL. It's giving them numbers. What is 035? So the very first thing that it does is it goes down here. All right, so branches, I'm going to guess that is a branch unconditional. And what it's doing is jumping to the end of this loop, loading okay, that stores the location of the oh, here we go. It says it finds the value of a field in the object whose reference is currently on the evaluation stack. Okay, great. So that's that. And then pops the current value from the top of the evaluation stack and stores it in a local variable at index 0. Store local 0. Okay. Branch S unconditionally transfers control to the instruction in short form, which jumps all the way down here. This is a great help for IL. Right on. Oh, perfect. Okay, let's bring that over here. Gonna keep that one in the back pocket here. Theme, dark. Okay, BRS unconditionally transfers control to target instruction in short form. Okay. So we come down here, we load the local variable at index 0 into the evaluation stack. Okay. Loads node. Finds the value of a field in the object whose reference is currently on the evaluation stack. Finds the value of a field. Load field int 16. Okay, so you have to specify the size when you load a field of a thing that is already there. Node we got from first. Then what we want to do is pushes the integer value -1 to the evaluation. That's interesting. I have no idea how that works. Okay. And then branch when two unsigned integer values or unordered float values are not equal. Okay, so this is this. So we have loaded the feature index by taking the reference that's on the top of the stack, loading the field, and then getting the leaf index, which is a constant, -1, and then branching. If we are true, we go to IL09, which says load arg1, which is the reference to the array. And then we say load location, loads the local variable at index 0 onto the evaluation stack. Node dot feature index. We loaded the arg at index 1 onto the evaluation stack. Okay, so load arg0, load field, which is value type. Decision tree first. I'm guessing that this magic right here is like basically converted to a constant in the JIT. So that's saying go and get me this field called first. Okay. And then this takes that, stores it at location 0. This is what we're calling node. Okay, location 0 is the variable node. So then we're saying load, go get me the field that is the feature index, load the -1 branch. What is UN? Transfers control to target instruction, short form, when two unsigned integer values or unordered float values are not equal. So this is basically saying not equal. All right, we have loaded the field, we have loaded the constant, we have then branched based on those two things. Now both of those should be popped off. Inside the loop, looks like it highlights side by side. Is it? Oh, it does. That's cool. Okay, this is great. All right, so now it says take load arg1. Arg1 is features. And put that onto the stack. Then load location 0, so whatever is in here, which is node. Load the field from the location, which puts the feature index on the stack. Loads the element. Oh, this is how you do an array access. This says loads the element with type float32 at the specified array on the top of the evaluation stack as float F. And I'm guessing that R4 means store it in register 4. So then this says, all right, so now register 4 contains F. And I don't see F in comments anywhere here, so I might not be correct about that. But I'm guessing that register 4 contains F. Or is it putting it back on the stack? Loads the element with the type float32 at a specified array index onto the top of the stack. Okay. What is the R4? Maybe R4 is defining the width. Load element R4. I think that's what that means. R4 is telling it that it's a float. Okay. Then what we're doing is we're saying put the reference to node back on the top. Load the field value. Branch less than. Branch anyway. All right, this is going to be, I don't think this is going to be that hard. Oh, R real. Yeah, that makes sense. That makes total sense. Okay, I really don't think this is going to be that hard all of a sudden. So let's just sort of write it out by hand and see if we can come up with what we want for the first one. And let's just do it as a comment here. We're just going to put this over on this side. And we're going to pull this over a little bit. And what we want this to end up being like is, okay, load. Let's just write the function that we want. This is like cheating. We can just write the function. This is like cheating. Okay. So we want basically a float eval, and this takes in a float array of features. And this says if Features 0 is less than 0.99999. In this case, the no return I'm just going to put an else here. Return this number. FF. Okay. Then, instead, we're saying go to 2, which is basically if features 17. I know this is going to take a hot minute to type it all up, but just so that we have like a reference to go off of here, I think this is worth the effort. Okay. Then we go to 3. Otherwise, we go to 4. Okay. Three 0 1. Nope. 2 1. 3. 3 is f2 less than 0.5. f2 0.5. Maybe good to put your if my yeah, good call. Okay. 3. One. Okay. If 3, then we go to 5. This is 5. Okay, this is 6. Need to be explicit about putting these F's here. Okay, that takes us to, this is 5. Inside the yes, we go to 9. Let me just collapse some of these. Okay, inside the yes, we go to 9, which looks like this. Okay, I'm new to this channel. What are we building and why all the float numbers and feature array elements? Okay, this is a great question. I have a requirement at work to basically implement a decision tree random forest. And I think the implementation is quite right. You're going line by line, but it's actually referencing lines in different order. I don't know exactly what you mean there. Quality coder. I have a requirement to basically implement a random forest in .NET. The requirements on this are largely like time-based requirements. The issue is that the previous implementation that we had was written in R, and it was ridiculously slow, like atrociously slow, unusable. What I need to be able to do is take 10,000 job to user combinations and evaluate them to get a probability of a click, and like all 10,000 need to happen in about 45 milliseconds to 50 milliseconds. And on those, the other requirement is that it all has to happen on a single processor, because this is going to run on a machine with a bunch of processors, but each of those processors has to be able to handle requests constantly because this is running on the web tier. So this has to be single threaded. It has to do 10,000 evaluations in 50 milliseconds. That's the long and short of the requirements. And so what we're doing right now is we have an implementation. We have an implementation already, and for 10,000 evaluations, we are down to about 130 to 135 milliseconds. We still need to improve by a factor of 3. These trees are currently stored as like arrays, and then we just sort of branch around in this array. Each node in the array represents an individual tree, an individual decision node. And so instead, what we're doing is we're going to take these nodes and we are going to create exactly a like an assembly and compile it, and then have it just basically the entire tree be a single function instead of having to reference data over and over. And the reason that this should speed things up is it's going to get rid of a fair amount of branching. There's a lot of branching right now at the very end of the tree. At the ends of the tree, it tries to it branches one more time to find out that it's a leaf, which we can instead just replace with a straight return value. And that's pretty much the goal. Another thing that this is going to help with a little bit, which I'm not sure is like particularly that important, is since we're moving all of this into instructions, we're now separating the instructions of the decision tree from the data of the features, which means that they're no longer competing for the same cache space, because instructions have their own registers and cache in the processor, and the data has its own register and cache at the lowest level, at least. And hopefully we gain a little bit of additional speed there. So I'm hoping that this just gets it to the point where it's like ridiculously fast, and this is going to be the end of it, and then we just go and like start implementing this and getting a test going. But yeah, that's pretty much what we're working on. All right, Hugo. I think the implementation is quite right. You're going line by line, but it's actually referencing different lines in order. I'm going line by line. I believe... so this is 3. When this is true, I immediately fall into here because the yes is pointing at number 3. Right? Then the yes of this is now pointing at number 5 right here. So I'm going straight to number 5. So is that what you mean? And then eventually I will come back and I will say, okay, let's do the else, and go do, number 4 and pop in number 4 down here. I guess I could go ahead and just like put the number 4 down there. So that we know later on. So this one goes to 3 or 4. And then this one goes to 5 or 6. Here's the 6. And then This one goes to 9 or 10. This is going to be really ugly by the time we get done. Okay, this one is 10. There we go. Now we'll do 9. Right, yeah, speed. I mean, that's the whole point here. That's the whole goal. Okay, so now we want to take this. We want to pop it in here. This is 17 or 18. 17. And 18. It's places like this where it's going to get really fast. So let's just go ahead and do 17 or 18. You know why? Because they're just return statements. Oops. Let's make this wider. Your first one says yes, but you go to 2. Good call. Yep, you are correct. Yep, you are entirely correct. Is that what you meant, Hugo? Thank you for pointing that out. Okay, so yes, no. No means go to 2. Okay, yeah. All right. Okay. Yes means go to 3 or go to 4. Okay, so we came all the way down here. We did this one. We did the yes. We did the no. On this one, we go to 10. 10 is this. I really need, like... I need a little place up here. Where I just store this. Okay, so 10 is 732 and 0.5. This is 19. This is 20. Okay. So F. Okay. 19 and 20. I'm sure some Linux guru would have found a way to regex. Yeah, probably. Well, funny enough, it wouldn't be that hard if we had actually parsed it into a tree to just like output some example. To just like run over the tree and basically append a string as we go. But I'm not going to worry about that. 6 goes to, oh, first we got to copy and paste this. Six goes to 11 and 12. 11 and 12. Okay, this number. And then 11. And 12. This is 8, 762. Okay, 21 and 22. 21, 22. Okay, 23, 24. 23, 24. Okay. Return. Just create a large map. Array. Oh, I see what you mean. And then we could just populate them all from it. We still have to do the code generation step, which I don't really want to do, so I don't mind actually just grinding away on this for a minute. It'll be over soon. So that's the point, though. We're not actually going to maintain this. This is going to be generated code from the trees. So in here, we have basically all of the decision nodes, and we're going to generate this code that I am doing by hand from this automatically, and then we're going to compile it into a function. And then we're going to use that function instead of actually calling the evaluate on this tree. We're just going to call this function that we create, and hopefully by getting rid of all of these feature lookups and all of this crap and basically replacing it all with constants and a bunch of if-then statements, this is going to get a whole lot faster. That is the plan. And we're just going to do it for each and every tree. So we're only doing this one by hand because I have never used, we're only doing this one by hand because I have never used the tool before that actually generates the code and emits the function. And so I want to basically create a reference example, get the IL from it, and then basically just try to copy creating the code that this thing creates. That's the plan. 4. And I think we're like, what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We're about halfway done at this point. So it shouldn't take too much longer. Go get our if then. Let's put the if then at the bottom. Okay. Gonna do if then on this one is 2, 0.5. Then we go to 7 and 8. 7 and 8. Oops. And then this for each of these. For this one, 734. And for this one, 27. Oops. Okay. Now we want to get to 13 and 14. 13. 14. I have lost it. Oh, there it is, 14. For this one, 15 and 16. Here's 16. Here's 15. Okay, each of these are decisions, so we can copy and paste this. 1, 2, 3, 4. This is 732. 0.0. Oh. 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 Oh, there we go. 0.5. This one is 285. And this crazy number. 734, 101. And 722 and 0.5. Okay, 25, 26. 25 and 26. 27, 28. I think we're at the end here. 27, 28. And 29, 30. And 31 and 32. Alright, that's it. All leafs. Okay. Now all I gotta do is put in these return statements. And then see if it complains. Already did that one. Get rid of this. I believe every single if then. Let's just see. Can I do var features equals var random equals new random grows equals enumerable dot range 0 to, I don't know, 850 or so dot select random.next. Oh, of course. That'll be way too easy. Dot to array. And then let's just do features, nope, eval features dot dump. That's interesting that it keeps coming up with exactly the same one over and over. Well, these are extremely small numbers. And that is an extremely big number. That's right, I don't have the distribution of these the same. Freaky. Which one is it hitting? Am I crazy? Which one is it hitting? 199 bunch. Oh, it's hitting this one. So only one in about 10,000 tries. Only about 8 in 100,000 tries are actually going to get past this the way that I'm doing it. So the way that we can fix that is we can say features 0 equal times equal 2. Okay. Half the time we get something else. Half the time we get that one. Okay, perfect. Super, super interesting. Now let's do it like this, and let's say var dt equals new dt decision tree. Nope, decision tree dot create. The hell did we call this? Example decision tree. Example decision tree. Okay. Var timer1 equals stopwatch dot start new for int I equals 0, I less than, I'm just gonna say 100,000, I guess. Nah, we'll just do 1,000,000. I plus plus. Eval features. And let's do something like var results. Well, putting it in perspective, the other one is doing hundreds of millions and is getting done in milliseconds, so I'm like, this is probably not even large enough to like get a reasonable measurement. I'm just hoping that there's a big enough difference for there to be something obvious about it. So results equals new float array of 1,000. And then we're going to say results of I mod 1,000 equals that. And then we're going to say timer1.stop. And then we're going to say the same thing, but for timer 2. Timer 2, results 2, timer 2, and this one is DT. DT.evaluate. And then we're going to say timer 1 dot elapsed dot elapsed dot total milliseconds dot dump, and this is going to be something like func. Then we're going to have timer 2 dot elapsed dot total milliseconds dot dump, and this is going to be DT. Any guesses? Holy cow. That is wildly surprising. Did you see that one time where it took a really long time? Well, the interesting thing is func is always the same time. Oh, nope, there it jumped up to 31. Let's do more. Let's just do 100. Well, that's taking some time. Crazy. That is surprising. God, that's surprising. Is this even... What? Oh, that's a good point. Yeah, this is definitely not in, like... That is a good point. Yep. Right. Decision tree test. Just kind of put it down here, I guess. Okay. There's all of that. Now we want to write a function. Now we want to write a test that basically does this. Okay. Public void test compiled func verse array dt verse dt. Okay. And I don't want to do this. I want to do it with the real data. So let's go get the real data. Actually, let's figure out why this is complaining, because there is no dump. That's why. All right, we'll come back to that. Let's go get the real data. Can I shrink this? Oh, there we go. That's what I'm talking about. Yeah. How do you get the data? Kind of crappy how you get the data. Did I not make a function to get the data? I suppose not. Okay. We're going to copy that. And we're going to get rid of this random features. I'm going to pop this in here. That gets us a bunch of samples. Then we're going to say for, something like 1,000,000 times. We're going to say no, not 1,000,000 times. We're going to do all of the samples. There are 10,000 samples. So we're going to do it 1,000 times. Samples dot count. I don't even want to do that. Samples. I think I just want to do. What the hell is the string? For s equal samples dot select m dot value dot toArray. Now that should be okay. Perfect. So now I'm going to say new float s dot length, and then I'm going to say eval. I'm going to say results. Okay, 4 underscore equals 0 underscore less than 100, I guess. Just check this in a moment. Underscore plus plus. Now we're going to say for I in results no, s dot length I plus plus pop this over. Okay, results of I equals eval s of I. I think that's it. I think that's all I care about right here. Actually, I don't even want to do this inside the timer because that allocation isn't super important to me. Okay, so this would be about 10,000,000 times. So now we're basically going to copy this. And this is dt.evaluate S sub I, timer 2 stop, and then we're going to say output dot right line func okay. DT is timer 2. Okay. .NET build C release CD space fast.modeling.test, and then we want to run this test called test compiled func versus DT. Test compiled func versus D. How did I spell that? D. Ah, shit. DT. Aha. Okay. All right. That was super important. Run it in a production release build. Run it in a release build. Just to make sure we're not crazy. Let's run it for longer and see if this holds up. How many times do we want to run it? We want to run it 1,000 times, because that'll take 10 times as long, but still less than a second each. Okay. Let's just think for a second about what just happened. We ran every sample through one tree, and we did it 1,000 times. There are 1,000 trees. I'm not entirely sure this is going to make a big difference on the bottom line, but overall it definitely seems to be an improvement. I think this is not going to be typical. I think there is a lot going on here. Like we've seen the DT number explode before, even in the other ones. So like if I keep running this, it's possible that DT number drops dramatically at one point. I gotta try it for just a little bit longer. I mean, it seems pretty consistent. I'll say that. Okay, I'm convinced it's consistent. Okay, so that's a huge improvement. 233 to 144. 141 divided by 234. That is about a 40% improvement. If we are at 135 times 0.6, ooh, that would get us to 81. That is getting really close. Okay, let's see if we can do this. We have about 25 minutes, and I have a hard stop today because I have to go to a meeting. Let's see if we can get it done. 25 minutes. There's also probably going to be some overhead with like the whole like emitting it part. Not 100% sure. Okay, so that was great for a test. So let's go like that. And then let's go void test thing. See how good I am at naming? All right, thanks for coming and hanging out, Quality Coder. I really appreciate it, and hope we'll see you around. And also, yeah, thank you so much for that. I really appreciate that. We've been working on this now for coming up on the end of 2 weeks, and I'm really hoping we get to our goal. Okay. var1 emit. Let's do void test compile tree. Okay. The two hardest naming problems in CS: naming things, cache invalidation, and off by one errors. All right. Let's take a little brain break for a second. Actually, let's not. Let's open up .peak and let's revisit this. Can I refresh this? Refresh. Can I tell it to refresh this, or does it just know? Where did we put that function? I think we put it in... Why is fast.modeling the only thing that came up? Oh. I didn't put it in fast.modeling. I put it in the test class, right? Give me this code, stack exchange, nope, culture, fast, test, bin, release, net core app, and it's got to be in this one. Dot test. What did I put in the root namespace? Oh. Decision tree test. Eval. Decision tree. Don't care about that anymore. Okay, eval. All right, that is a lot. That is a lot. But it seems really simple, right? It is literally just like 5 instructions over and over and over and getting the instructions right. Does not seem hard. And it's just dumping a bunch of constants all over the place. This is exactly what I was hoping for. It was in the test class. Actually, would it be more accurate to put the test implementation in the XGBoost class? I mean, in all likelihood, this is just going to get deleted as soon as we finish like building this out, and then the actual like tree construction I think is going to go right into the decision tree class itself. And then there'll just be like a .compile function on the trees, something like that. Oh, for the timing comparison? Yeah? Yeah? Does that matter? I wonder if you have something like this, if you turn it into a ternary, if it gets faster. Right? Let's take a look at this right here. This is feature 6. This is this one. Wait, what the hell is it doing? Oh, see? So it does a branch right here. $39. No, nothing branches to the 39. It just falls through. So maybe there's not anything going on there. So you would just return that. Pushes a supplied value. Right. This is pretty long. Okay. Starts at the root. And then all we have to do is basically create tags. And these tags can have names that are basically uh, node underscore whatever the node number is. So this would be like node underscore 0, node underscore 2, node underscore 1, and those would just be the label names that we want to branch to. And wherever we are ready to start dropping the code for them, we say mark. So wherever we start doing okay, yeah, this is not going to be hard at all. I think. I keep saying really like blatant stuff like this isn't going to be hard. Probably don't want to branch for return statements. I don't know how to avoid that. At the very end, do we have a return? Yeah, right. So there's no branch per se for the returns. It's a branch on the last decision to choose which return to go to. Is there a conditional move? E1 dot con move load constant load. There's no conditional move here. Break. Oh, hello, Zenith. This is not a code editor. Is there like a... I don't even know. Is there... Options? Options. Yeah, no, there's nothing here. This is dot peek. That basically lets us look at... Hey, what's up, everybody? Appreciate you stopping by. This is just .peek that basically takes this code that we were trying to look at and get an example for what the IL instructions are. And then the idea being that we're going to take this string, generate this function using all IL. Using a library right now called Sigil. And I'm definitely going to run out of time because there's only 17 minutes. But we're going to try anyway. Don't peek too long. Okay. We have a function. We need a tree. Decision tree. DT. Okay. Now what I want to say is var stack equals new stack of decision tree dot decision tree node, and then I want to say dt var nodes equals dt dot nodes. I don't really need that one. And then I want to say stack dot add dot push because it's a stack. Push dt dot nodes 0. All right, while stack dot empty count. Yeah, count is greater than 0. Do this thing, and then I want var delegate equals e1 dot delegate, create delegate. And this is actually going to be a function of, it's going to take in a float array and return a float. Create delegate. Do I actually care about that stuff? No. Not that I think. There we go. And then return del. Now I'm just going to do the test right in here. Okay. So that's the decision tree. How do I make the decision tree? .create. We're not even going to pass it in. Screw that. We're just going to go like this. That's the decision tree. Those are the nodes. We push a node on there. Now what we need to do is basically say now what we need to do is take the true branch and the false branch and push both on there. Okay, so this is not going to just be a decision tree node. This is also going to be e1.create label, define label. And this is going to be node underscore 0. Define label, label, and decision tree node. Now we're going to say push the label and the decision tree node. Okay, now while the stack.count, now we're going to say var label dt node equals stack.pop. Then we're going to say e1 dot mark label label. Then we're going to say if no, now we're going to start emitting. Alright, we have marked the label load arg1. So we need to load the reference to features. Then we need to load whatever the hell this constant is. Then we need to load the feature value. Then we need to load the feature value. Then we need to load a constant. Okay, so if it is a leaf, we just want to load the value and return it. So let's do that one. Mark label if node dot feature index equals -1. Then we're in a leaf. We're in a leaf. Do a return. else create the if create the branch, check it against create the child labels, create the branch, push the children. Yeah, I think that's it. Alright, we're in a leaf, so do a return. So in this case, I need to load the value. So load a constant e1 dot load constant, and this takes in anything I want it to take in. So this is node dot value e1 dot return. Okay, that one was simple enough. Load the constant, return. Otherwise, load the features, load the features, load arg0. We're just going to do this one by one. Var left label equals e1 dot create dot label, make labels, define label, node underscore plus node dot left branch, true branch, var right label equals e1 dot define label node underscore plus node dot false branch, create the branch e1 dot load argument 0 e1 dot load constant. The constant is node dot feature index e1 dot load element, that's a float, dot e1 dot load float, nope, load element, type of int, nope, float. There's now that float. Load a constant, which is the value, and then branch. Why are these all branch greater thans? That's freaking me out. I think I'm just going to go with a branch less than and let the JIT handle it for the time being. See if we can do that. E1 dot branch less than, branch if less, to the left label. How do I tell it to go to the right label ever? Does it just fall through? Maybe that's why the greater than is there. Branch if greater. Right label? Okay. I feel like there's 5 arguments. Oh, I didn't load the element. I gotta call load element. No, I did. I loaded the element. Oh, then I gotta load the constant of the value. Load element. E1.load element. Load constant of node.value. Then branch if greater to the right. Now I want to say stack.push left label and node dt.nodes of node.left.true branch. Like that. And then stack.push right label dt.nodes node.false branch. I think that's it. I like literally think that's it. I have no idea how to tell. Is there a way to get the IL out of it? Well, there is a really easy way to do it, which is we just run it against our eval function. Okay. I think Sigil will emit the IL and maybe even the C# for it. Okay. E1.emit. Nope. IL. Nope. What's it? Del dot. Nope. Emit dot. No. Okay, I'm not going to worry about it for now. I'm just going to run it against the thing and we're going to see what happens. Random features. That's our features. And then basically what we're going to do is say del of features dot dump del, and then we're going to say eval of features dot dump eval, and this is test compile tree. Those are different. Alright, one of them is always returning the same values. Okay, well, it's 2 o'clock, and like I said, I have a hard cutoff today, so I do have to run. When you commit all of this, mind adding the... Yeah, I'll just drop the link pad script in there right now, and I'll go ahead and update it. Code. Uh, Zizith? I think that's how to say that. Thank you for the follow. I really appreciate that. .NET culture fast. Let's put it in. I'm going to put it in the modeling test. Yeah. Try sigil func. And let me go ahead and get that committed. And we'll be on our way. Fast. Commit. I believe I'm on master. More stuff, including sigil attempt. Commit and push. All right, there you go. It's pushed up there. You can find it on my GitHub. And again, thank you everyone. It's going to be in /fast, not in JS13K. But yeah, thanks everybody for joining, and I hope you had a good time. Real fast, we're going to raid somebody, which is going to be Raimu. We're going to raid. No, we're going to raid the Michael Jolly, who is just getting started. Maybe we're not. Maybe he's not just getting started. Just kidding. We're going to raid Raimu. I think Raimu today. Oh, none of these people are actually doing anything. RHY Mu. RHY Mu. Oh, there he is. Okay. All right. Everybody say hi when you get there. Thanks, everybody, for joining. I will be back tomorrow at noon, and we'll do this all again, noon Eastern time. And thanks, everybody. And, yep, in about 10 seconds here, we'll make our way over there. Here we go. See y'all.